Welcome everyone. Let's just dive right in. So, if you're gearing up for the OCAP or your written boards, you probably already know that optics can feel, well, kind of like a daunting, purely theoretical subject. But I want you to reframe that. Think of optics as the grammar of ophthalmology. You use these rules every single day in clinic. Mastering these basic points and planes isn't just about passing a test, right? It's the absolute secret to truly understanding what is actually happening inside your patient's eyes. This explainer is essentially your clinical optics masterclass. We're going to lock this down together.
Here's our quick roadmap for today. We're starting with mastering the cardinal points, then nodal points and lens axis, clinical refraction and the eye, navigating the focal planes, and finally, the minus lens board trap.
All right, part 1, mastering the cardinal points. Let's build that foundational vocabulary.
First up is the primary focal point. Now what you really need to anchor your brain to here is the concept of zero vergence exiting the lens. Imagine you place an object exactly at the primary focal point. The light rays emanating from that object hit the lens, and the lens bends them so they leave completely, perfectly parallel. They have absolutely zero vergence, so this is the exact location in space where diverging light becomes parallel light. Simple as that.
Now contrast that immediately with the secondary focal point. Do not confuse the two. It's a classic mistake. The secondary focal point is the exact opposite scenario. Here, we've got parallel rays with zero vergence, already traveling toward and entering the lens. The lens bends them, and that precise location where they converge to form an image, that's the secondary focal point. So just remember, primary is about parallel rays leaving, secondary is about parallel rays entering.
And this brings us to the nodal point, which we usually denote with an N. Listen up, because this is a massive OCAP hurdle. I like to think of the nodal point as the VIP lane of the lens. Any ray coming from literally any angle that hits this specific point gets to walk straight through, completely undeviated. It won't bend at all. When you're stuck doing ray tracing on an exam, the nodal point is absolutely your best friend because it requires zero math. It just goes straight through.
Moving on to part 2, nodal points and the lens axis. Let's put this into physical space.
Okay, examiners absolutely love to test your transition from theoretical physics to clinical reality. Notice the contrast we have here. A thin plus lens is really just a theoretical construct. We use it to simplify teaching, right? Its two nodal points occupy the exact same spot in optical space. But real lenses, the thick lenses you actually prescribe in clinic, contain two distinct nodal points. The clinical reality of this is that a ray entering the first nodal point will actually visually jump to the second one and then exit at the exact same angle. It's still undeviated. Keep that thick lens jumping ray in your mental model. It's a great board trap.
So with all that, how do we actually define the lens axis? Well, the lens axis is simply the specific ray that passes straight through both focal points and the nodal point. Because we know it goes through the nodal point, we know it passes completely undeviated. It is the ultimate straight shooter of the entire optical system.
Section 3. Clinical refraction and the eye. Let's make this biological.
Okay, I want you to actively recall what we've just covered for a second. Here is a classic OCAP-style bonus question. Picture an eye where parallel incoming light enters the cornea and lens, but the secondary focal point physically lands behind the retina. Is this an emmetropic, hyperopic, or myopic eye? Pause for a second, think about it, and lock in your answer.
All right, the diagnosis is a hyperopic eye. Why? Well, the tip-off is exactly what we defined earlier. The secondary focal point is located physically behind the retina. If we look at the pathophysiology, the converging power of this patient's cornea and lens is simply too weak for their specific axial length. So what's our clinical pearl? How do we manage this? We add converging power. We place a plus lens in front of the eye to pre-bend those rays, physically pulling that secondary focal point forward until it rests perfectly on the retina. It's anatomy matching physics perfectly.
Part 4. Navigating the focal planes. Let's expand this out a bit.
To truly understand the primary focal plane, we have to expand our mental model from points to planes. We already know the primary focal point makes rays exit parallel to the central axis. But a primary focal plane is a whole flat sheet extending outwards from that point. If a light ray emanates from literally any random spot on this plane, the rays will still exit the lens parallel to one another. The only catch? They just won't necessarily be parallel to the main central lens axis.
Now, this beautifully sets up a foolproof clinical algorithm for tracing rays on a test. When you're asked to determine the exit direction of rays coming from a point on the primary focal plane, just follow these 3 steps. Step 1, identify the single ray from that point that goes directly through the nodal point. Step 2, remember your golden rule. That nodal ray passes through completely undeviated. Draw it straight. Step 3, take all the other rays coming from that point and simply draw them exiting the lens exactly parallel to your nodal ray. You do not need to calculate any complex refraction angles. The nodal ray does all the heavy lifting for you.
Similarly, we have the secondary focal plane. If the secondary focal point is where parallel rays exactly on the axis converge, the secondary focal plane is basically the home location of all images formed by parallel rays hitting the lens from any angle.
And you know what? We can use that exact same nodal ray anchor trick to find where images land on the secondary focal plane too. Step 1. Look at your incoming bundle of parallel rays hitting the lens from some oblique angle. Step 2. Imagine a single ray traveling parallel to that bundle that happens to pass perfectly through the nodal point. Draw it straight through, undeviated. Step 3. The exact point where that undeviated nodal ray hits the secondary focal plane is your destination. That is exactly where all the other parallel rays in that bundle are going to converge to form the image. If you master this nodal ray trick, I promise you, you will never miss a ray tracing diagram on your boards.
Finally, part 5. Let's talk about the minus lens board trap. I really want you to commit this high-yield comparison table to memory. In a standard thin plus lens, the primary focal point is in front, and the secondary is behind. But in a minus lens, the physical locations are entirely reversed. F1 is now behind and F2 is in front. The memory trick here is incredibly simple. Whenever you see a minus sign, physically flip your mental map 180 degrees. The planes swap locations entirely.
And here is the crux of the minus lens clinical correlate. The fundamental definitions of these points never, ever change. Only their geographic location in optical space changes. Rays associated with the primary focal point still exit the lens parallel to the axis. Rays associated with the secondary focal point still enter the lens parallel. The physics remains totally constant. The classic board trap is simply forgetting to flip your F1 and F2 geography when you start tracing a minus lens. Don't let them catch you on that.
So I want to leave you with a final, slightly provocative thought to connect this all back to your daily clinic. We know a myopic eye has too much converging power, right? Which means its secondary focal point lands in the vitreous, somewhere in front of the retina. Knowing that a minus lens structurally reverses these focal plane locations, causing light rays to diverge rather than converge, how does this beautifully simple piece of optical physics directly allow you to manipulate the focal plane of that myopic patient, pushing the image perfectly back onto their retina? I want you to visualize those diverging rays the next time you write a minus prescription. Thank you for joining this explainer. Keep these foundational rules in your back pocket, and you're absolutely going to dominate clinical optics.